Okay, welcome back everyone. Today we're going to be doing an interesting problem, and it's actually fairly basic. It's just a derivation of the area of an ellipse with calculus. So I actually got inspiration to do this video from this random clip that popped into my recommended list, and this clip was entitled Mathematical Genius, and it was basically a clip from the movie called Rushmore, of this kid going up to the board and supposedly being a genius and solving, this problem that was supposedly extra credit, but the teacher put it up as uh, a joke, apparently. Now, obviously, it was exaggerated. You can see the clip for yourself. I'll put it in the description. But I thought it was pretty fun to actually do this problem because I never considered it to be, a tough problem. So yeah, I'll just quickly show that it's not too bad. Okay, so let's start off with kind of visualizing what we're getting ourselves into. And by the way, what we wanted to strive for is the area is equal to pi AB, where A is the semi-major axis, and B is the other major axis. So in other words, we can visualize an ellipse as such, and where this length is A. So here we can think of this as the center of our ellipse, and this here is B, and again we want to show that this is our formula for the area. Now to start off, well, we have an elementary obviously form for all the points that lie in the perimeter of the ellipse, and that is just that they abide by the following formula. We have x over this axis here, so this radius A, plus y over this radius B squared is equal to 1. So this is the general form for an ellipse that we have all learned in the past. Now, what I want to do is I'm going to solve for y so that we can get an explicit formula to actually integrate. And before I do that, what we are trying to get to is, again, we want to find the area of this ellipse. So whenever we get that plus or minus, we can kind of neglect that and just make it plus, such that when we integrate, we actually keep the entire area. So I'll just quickly show what we want to get to. So if we subtract x over a squared on both sides, we get, and also we'll directly multiply both sides by b squared, and then take the square root, we get y equals plus or minus b times the square root of 1 minus x over a squared. Okay? So this is our general form, but when we integrate this, we don't want like these things to cancel out, right? So we can just consider the upper half, just the upper half, which would just be the positive part, and then we multiply that by 2. So if we take the absolute value of both sides, this negative goes away. So in other words, what we can do is when we integrate both sides, we're gonna get, well, following integral, and notice that this is going to be minus a. We're assuming it's centered at the origin without loss of generality, and this is a. So we're integrating from negative a to a, and we take out the constant b and multiply by 2 to get this. So square root of 1 minus x over a squared dx. Okay. But notice that this is an even function. We can reflect this half over the y-axis, and it'll directly line up with this half, right? So, in other words, we can further simplify this by taking this and putting it to 0, right? So we're integrating from 0 to a, but multiplying by 2 again. So actually, this just becomes this 4b times the integral from 0 to a of the square root of 1 minus x over a all squared dx. Okay, so now we're left with this integral, and it's actually a fairly elementary integral. And what I'm going to start with is I'm going to make a little bit of a small u substitution. So we're going to make u equal x over a, so that means du equals 1 over a dx. Okay, So now if we substitute this in, well, this goes to u, and then we get this du here. We have an extra a on the outside, so we're going to get 4ab times the integral from, and now we plug in now we plug in our bounds. So when x equals 0, u still equals 0. So, and then when x equals a, we just get 1. So that's pretty nice. And now we actually get a very nice form of 1 minus u squared du. Now this is an elementary trigonometric substitution problem. And the substitution, well, we can quickly see how we get the substitution. So if we have a right triangle, where this is our angle theta, then using the Pythagorean theorem, this side can be 1 minus u squared. This side can be, well, this side can be u, and this side can be 1, right? So what we want to get is, well, notice that cosine of this angle, and again, some background for why I'm doing this. I'm doing this because, well, notice that if we take the square of this and take the square of this, we get, and then take the square of this, it all works out by Pythagorean theorem. And if we want to make this as simple as possible, so the most simple way we can evaluate this is, in this case, well, we can technically swap the u and the square root, and then we can use sine, but in this case, we might as well just use cosine of theta. So this is our trigonometric substitution. Cosine of theta equals u. Exactly. And then, thus, du is equal to minus sine of theta, d theta. So plugging this in, and we won't worry about our balance for now. We'll worry about, or, well, you know, technically we can, well, we could use our balance right now. So, yeah, well, why don't we do that? So, if we have u is equal to this, well, if we have u is equal to this, we're just going to have 0 equals cosine theta, and that implies that we have theta is equal to pi over 2. And then if we have 1 is equal to this, well, we just have cosine theta is equal to 0 is equal to 1, so that means that theta is equal to 0. Now we get it kind of messed up, but notice that we get this minus out front. So what we're going to have is minus 4ab times the integral from, yeah, this weird thing, so pi over 2 to 0, and the square root of 1 minus cosine squared, cosine squared theta, d theta. But by some properties of integrals, we can erase this negative sign and then flip our bounds. So that this just becomes 4ab times the integral from 0 to pi over 2. And then the square root of 1 minus cosine squared, well, the whole reason we did this is because 1 minus cosine squared is known to be sine squared. Oh yeah, on the outside we still get a sine theta. So in other words, we're literally just integrating sine theta, d theta, or sorry, sine squared theta. And now that's a pretty well known integral, but we can quickly solve this, and we use the fact that, well, sine squared theta is equal to 1/2 times 1 minus cosine of 2 theta. Okay, so now we'll also take the 1/2 on the outside, and we'll get 2ab times the integral from 0 to pi over 2. Actually, we'll just directly do the integration, since these two integrals are fairly trivial. So what we'll have is, well, the integral of 1 is just going to be theta in the theta world. Then we have the integral of minus cosine. Well, that's just going to be minus 1/2 sine 2 theta. And the reason being is that you can think of this as a small u substitution, where we let u equal 2 theta. We get an extra 1/2 on the outside, and we keep the inside, right? And obviously, yeah. So we evaluate this from 0 to pi over 2. Okay, so now it's just some basic stuff. What we're going to have is, when we evaluate at pi over 2, we're going to get pi over 2, and then sine of, well, we're going to get pi, so we're actually just going to get pi over 2 for our first part, because sine of pi is 0. And then subtract from that, well, 0, sine 0, 0, so we just get 0. And multiply this all by 2ab. However, the 2's cancel, and finally we're left with ab pi, which is what we wanted to get. So that's pretty much it. And as you can see, we took a seemingly difficult calculus problem and made it fairly easy. So I hope you enjoyed that, and I'll see you in the next video. Bye. Oh, and by the way, Q, E, D, quaerad demonstration.